Hello and welcome back to section 4 of the course called Scaling Our Microservices Architecture. In this section, we will see what are the basic principles we should follow to create systems that are scalable and can adapt to increasing traffic patterns. We'll also see some of the common problems that services have to solve and how some approaches can help us leverage their use between all our services. In this section, we will cover 4 basic parts. We'll start by introducing some basic concepts that will help us understand how we can make our systems more scalable. For example, we'll see how a microservices architecture facilitates scaling of systems and why minimizing the sharing of resources between systems can make scaling much easier. We will then discuss a related concept, that of service discovery. We'll explain what are some of the complications around communication between services as the number of services grows in our architecture, what are the alternative options we have, and what are the pros and cons of each one. In the next topic, we will expand on some of the concepts we will have introduced on this section by implementing auto-scaling for our catalog service using an AWS service called EC2 Autoscaling. In the last part, we will explain what a service mesh and an API gateway is, what are the problems they solve, and where each approach is more suitable. In this first part, we will explore how we can make our systems more scalable, so that our architecture can easily cope with gradual and sudden increases in traffic. A major benefit of the microservices architecture when compared to a monolithic model is the ability to scale your various systems independently. I'll try to illustrate what that means through an example. In a monolithic system, we would have multiple components for each one of our business capabilities, all of them deployed as a single service. This means that if, for instance, a very popular song got published and we see increased traffic from customers searching for this song, we would need to scale our catalog and discovery components. However, since everything is deployed as a single unit, deploying more units of our service means that the other components would be underutilized. To overcome this limitation, we could split our monolith into different services, one for its different business capability. In this way, we would be able to scale independently only the parts of the architecture that face increased demand. We've been talking about scaling and scalability a lot until now, but what do these terms actually mean? Scalability is the ability of the system to handle growing amount of work. As we'll see here, there are 2 main approaches of scaling a system: vertical scaling and horizontal scaling. Vertical scaling is when we make a system capable of handling more work by adding resources, like increasing the memory available or the number of processors. For instance, we could start with a single server for our service, having a single core and 2 GB of memory. When our traffic increases, we can replace it with a more powerful server, having 8 cores and 16 GB of memory. We can keep doing that as our traffic keeps increasing. There are 3 main problems with this kind of scaling. First of all, because of physical limitations, there is a limit over which we won't be able to scale our system further following this approach. Secondly, this approach is very costly, since costs increase exponentially as we move to more and more powerful servers. And lastly, we have a single point of failure, which means that if something happens to our single machine, we won't be able to serve a single customer. A second approach is horizontal scaling, where we make our system capable of handling more work by connecting more instances of the same limited capacity. For instance, we can start with a single server of 1 core and 2 GB of memory, and as our traffic grows, we can start adding more servers of the same type to our fleet. As you can imagine, theoretically, this approach should be able to scale infinitely by adding more and more servers. In practice, there might be other limitations that make infinite scaling non-feasible, but still, this approach has much greater potential than the vertical scaling. Furthermore, having many of these cheap commodity servers is usually less expensive than having a single high-end server, and much more reliable. The key takeaway from the previous slide is that horizontal scaling is preferable to vertical scaling in general. However, we mentioned previously that there can be some practical limitations for horizontal scaling as well. So we'll try to elaborate on this now. Let's say we have a service consisting of two servers and a relational database. Our customer base grows and so does the traffic to our service. As we explained previously, we increase the number of servers to scale our service. As a result of this, the requests from our users are now split between more servers, so our service can cope with the increased load. However, as we can see, all the servers end up using our single database, which is an obvious bottleneck. So after a point, we'll realize that increasing the number of servers does not increase our capacity, because we've reached the limit of our database. There are several approaches to mitigate this, such as using the approach of vertical scaling, or using a master-slave approach, where applications write to a database instance but can read from multiple ones. However, in most of these approaches, the servers have to share a single component. For example, even in the master-slave scenario, all servers must write to the same master node. This sharing limits the ability of our system to scale horizontally. In order to leverage horizontal scaling, we'll have to keep our architecture from having a single connection across the whole system, what is usually called a single point of failure. This kind of architecture is usually called a shared nothing architecture. Looking back at our example, in order to achieve that for our database, we would have to split our dataset across several servers, a technique called sharding or partitioning. By doing that, no matter how many data we would have to store, we could just add more servers to our database fleet, increasing our capacity. On top of that, requests from the application servers would now be distributed among all these servers, depending on which data they access. This is a practice followed by several distributed data stores, such as DynamoDB or Cassandra. However, as everything in software, this comes with its own trade-offs. For instance, distributing our data across servers means that executing transactions or performing queries that join datasets becomes more inefficient. Assuming that we've already have decided to scale horizontally our service, having a fleet of servers, we still have to find a way to distribute the incoming requests between our application servers. This effort to distribute the requests between servers as equally as possible, so that we can utilize all of them, is called load balancing. The load balancer is the component that will receive the request by the customers, select one of the application servers to forward the request to, collect the response, and pass it through to the client. Next request comes in, and the load balancer will probably pick a different application server this time. There are different algorithms for choosing which server to send the request to. We don't have time to look at these algorithms now, but feel free to invest some time in reading about them. Of course, in the same spirit of our discussion so far, it's important to make sure that this load balancer does not become a single point of failure. Also remember that the traffic will probably be so big as to require multiple application servers to handle it, so a single load balancer server might not be enough to cope with it. Implementing that is a serious undertaking, but cloud providers have services for load balancing that are under the hood composed of multiple servers, which means they can handle very high load and are resilient to failures of a single server. We'll demonstrate how we can leverage such a service later in this section. In the beginning of this course, we discussed the contribution cloud computing had in the adoption of the microservices architecture. Autoscaling is a method enabled by cloud computing, whereby the resources of a service are automatically adjusted depending on the current load. In order to understand what benefits autoscaling brings, we'll have a look at the processes followed before the rise of cloud computing. Before cloud computing, buying a server was a process much more tedious and time-consuming. As a result, teams were observing the traffic of their services through time, calculating the number of servers they would need to be able to handle the peak traffic. This was a process called capacity planning. However, that meant that when traffic was lower than the peak during the year, most of these servers would be underutilized, so they were essentially wasting money. This approach had another pitfall. As we said, engineers were calculating their capacity based on traffic trends so far. However, sometimes unexpected things happen. This means that if traffic rised past expectations, their servers would not be able to cope with it and would start failing requests. What people sometimes did to avoid this is adding more headroom when making their calculations to account for these unexpected events. Of course, this meant that they were wasting even more money in order to be safe instead of being sorry. The advent of cloud computing made provisioning of a server a much quicker process though. People are now able to have an additional server in a matter of minutes, if not seconds. As a result, they can provision just as many servers as needed to handle the current traffic, release them when traffic goes down, and provision them again when traffic goes up. Autoscaling is a mechanism that allows systems to do that automatically, based on several conditions that can be defined. So, autoscaling enables applications to be much more cost-efficient and resilient. Later in the course, we'll see how we can use autoscaling in practice. In this video, we went over some of the problems that arise when trying to scale our systems and what are the main approaches we can follow.